Welcome to what is one of the final units that we will be doing this year, integrals, looking at area between two curves, and volume. So let's start out with something basic. If f of x equals x plus 3, find the exact area under the curve from 1 to 4. So I drew a line representing x plus 3, and if I want from 1 to 4, I know that I have here to here. I want the area under that curve, right? And so this creates a trapezoid. We have four sides with a non-parallel side here. So this point is 1, 4. How do I get that? Well, 1 plus 3 is 4. This is 4, 7. And so therefore, the area of a trapezoid, we have the formula here, 1/2 base. The base is 3 times height 1, 4. Plus height 2, 7. And so we're going to get 33 halves. And if you did the integration of that, of x plus 3 dx from 1 to 4, you would get x squared over 2 plus 3x from 1 to 4. And you would notice that you would get 8 plus 12 minus 1 plus 3. You get 20 minus, that should be 1/2 there. 20 minus 7 halves, which is 33 halves. So you could do it one of either way, trapezoidal sum or the integration. In this case, f of x equals x squared, we definitely could not do it. Could not do a geometric sum because we have a curved top. And so therefore, integral of x squared from 1 to 4 dx, which equals x cubed over 3 from 1 to 4. And so you get 4 cubed, which is 64 over 3 minus 1/3, so we're going to get 63 over 3. And so, hopefully, that is nothing new to you. But the question is now, what happens when we're looking for the area between two curves? This area right here. Well, how do I find that area? Well, first of all, you take the quote top curve, this curve right here, and subtract it from the function that is underneath it. And the key here is knowing these bounds right here from A to B. And so just so you see what's happening, I'm looking for this area minus this area. And so where do you see that? Well, all of this is the area under the curve minus this area that for some reason is not showing up. Maybe this will go over it. There we go. This area. And what I'm left with then is the area that's in between here. So if I take all of this green minus this yellow, I'm left with the area there. And so this will work anytime when you have two functions that are bounded by an a and b, the x values. So if we look at this one, we have the area of the region bounded by y equals x plus 6. That's clearly this one. And y equals x squared, which is this one. Then, and we know that we're bounded 0 to 2. It's as easy as 0 to 2 of the top curve, x plus 6, minus the bottom curve, x squared, dx. Now, you would need to know how to do this with math without a calculator, but there's a simple way to do it in the calculator. If you put that into y1 and y2, and I'll show you in class, you can do this out using the FNINT function. I think it's under Math 9, I believe. If you use that and you do it out, you will get an answer of 34 thirds. Now, just so you guys know that we're bounded, so we're looking for all of this area right here. Should have made that clear to begin with. All that area. So what we did is we took the area from underneath all of this and we subtracted this area, hence why we got how we got that integral. So this is again y1 minus y2, and I'll show you in class how to do that. Find the area of this region. The key here is that what don't they give you? They don't give you bounds. And so you must find the bounds. If you don't have a calculator, how do you do that? Well, you set x plus 6 equal to x squared. And when you do that, subtract over what the x plus 6, we get minus x minus 6 equals 0, x minus 3, x plus 2 equals 0. And so you know our bounds are now -2 and 3. And so, top curve, the integral from -2 to 3, the top curve, x plus 6 minus bottom curve, x squared dx. Again, put that in your calculator and you get 125 over 6. And I'll show you how to do that in class. So again, top curve minus the bottom curve. Same idea here. Why don't you just take a minute, set it up. You don't need to solve it. I'll give you the answer, but set it up. And so hopefully you got that integral. Again, top curve minus bottom curve. And so for our last example here, we're going to do it two different ways. If we look at this example, the region bounded by y equals x minus 2, clearly that's that line, y equals x minus 2. What's different about this one is that you have x equals y squared instead of y equals x squared. And therefore, if we solve for y, we're going to get plus or minus the square root of x, meaning that this is y equals square root of x, and this is y equals negative square root of x. And what I want you to notice here is that the area that we're looking at that's bounded is this area right here. Well, there's an issue. The issue is that when we start going from 0 to 2, let's see, what is that? We probably should have solved for that. So let's solve for it. We're going to go x minus 2, plug in for y, so x equals x minus 2 squared. And so we know this is at 4, comma 2. So we know we're looking for the bounds of 0 to 4 here. But here's the issue. What is our top curve? Well, top curve is y equals square root of x for sure. There's no doubt about that. From here to here, that's always y equals square root of x. But notice what happens. We have our bottom curve here, and then it stops being our bottom curve. It then becomes a different line. So we're actually going to split this up right there into two separate integrals. We don't have a top curve and bottom curve that's the same like we used to. And so therefore, we're going to split it up, and instead of going 0 to 4 of top minus bottom, we're going to have to split it up differently. We're going to split it up from 0, and where do they intersect? Well, I'm just going to tell you they intersect at 1. You could have figured that out. From the top curve, square root of x, minus the bottom curve, negative square root of x. And then you have the other function here, plus the integral from 1 to 4 of the top curve, square root of x, minus the bottom curve, x minus 2. And you'll notice that I forgot my dx here, so forgive me, please. So now, if we did that out, and I have the answers here, 4 thirds plus 19/6 equals 9/2. And that would be the area of the shaded red region. Do you agree, though, that that is more difficult because we have to split it up into two bounds? So what I want you to do is, even though we have the answer and we found it correctly, let's flip the page and let's look at how we can do it a little easier. I want you to think of it, instead of going bounds 0 to 4, like we looked at before, we're now going to look at integrating with respect to y. And what that means is, instead of going left to right, we're now going bottom to top. And we're looking at finding the area from here all the way up to here. And instead, we're going to be looking at our y values. Why is this nice? Well, we now have our top curve, the farthest one out to the right. This top curve is our top curve minus our bottom curve, because the way we want to look at this is kind of flip it so it's on our y. We want to flip it so this is our y-axis here and this is our x-axis. And if we do that, we get something that looks like this. And if I flip it correctly, more like that. So now we basically have a top curve and bottom curve. And so what we need to do with integrate with respect to y, we need to get everything in terms of y. So right here we do have x equals y squared. That's good. We have to get it into x equals here, so y plus 2. Now we have our top curve, x equals y plus 2. We have our bottom curve, x equals y squared. And now we can set up our integral, except our integral must be in terms of y. We've got to figure out what these y values are. Well, we already know that this x value is 1. So if I plug 1 in, here I get 1 minus 2 to get negative 1. So that's negative 1. And I already know that this is 4. So if I go 4 minus 2, I know that this is 2. So now I'm going to integrate from negative 1 to 2 of the top curve, y plus 2, minus the bottom curve, y squared. And now instead of putting dy or dx, I'm going to put dy. In your calculator, you're going to keep this in terms of x, okay? Don't think that we have to change that. We'll keep it in terms of x, and you will notice that when you do that, you will get 9/2. And so this way, we now don't need to split it up into two separate integrals. We can just look at it from the most right curve minus the most left curve. So again, instead of looking at it going from up and down, we now look at it going left to right. And that's it. I'll see you in class, but we got to get the joke. You will like this one. What do you call friends who love math? Algebros. Algebros. It's a good one. I know you've missed my great jokes. Anyways, see you in class.